Welcome back to another video on IMO 2023, which was just held in Japan last week. In this video, we'll be taking a look at the Day 2 problems, including a monster geometry problem for problem 6. So before taking a look at the solutions, I have some photos from the event to show you. So these photos are taken from the IMO 2023 webpage, and over here we have some photos of the contestant waiting to enter the exam hall. And the exam hall, wow, that's a really big examination hall. There's about 618 contestants for this year's IMO. So that's why they need a really big exam hall. And after the contest, the contestants had a great time having an excursion to Tokyo Disneyland. And they also had some workshops on various things like origami and tessellations, as well as Japanese traditional cloth. And also, I think there's also a tea ceremony that they could also experience. So at the end of the video, I'll also go over some statistics on how the contestants have done for this year's IMO. But before that, let's take a look at the problems. So for problem 4, we have an inequality problem. It's an algebra problem over here. So let x1, x2, to x2023 be pairwise different positive real numbers such that an defined as the square root of x1 plus plus xn times 1 over x1 plus plus 1 over xn. This thing is an integer for every n equals to 1 until 2023. We are supposed to prove that A2023 is bigger than or equal to 3034. Okay, so for this problem, I think the first observation that you really need to do is to notice that the an is increasing, because if you have this expression for an, then the next term an plus 1, you will be adding a xn plus 1 and adding a 1 over xn plus 1, and that will make it strictly bigger than an. And because we want all the ai's to be integers, then the an basically forms a sequence of strictly increasing integers. But that's not enough to show this inequality here, because then you might get 1, 2, 3, 4 until 2023, but you need to show that this A2023 is bigger than or equal to 3034. And this suggests that we need to introduce or force the existence of gaps in our sequence. So you cannot have consecutive integers. And this leads us to consider the following. So for the proof, what we'll be doing is, let's take a look at an squared, and suppose an is equal to the integer k. Then the question is, how does an plus 1 compare to an? Is it going to be 1 larger, or must there be a gap from an plus 1 to an? So let's, for easy notation, call this thing C and call this thing D. And now we introduce the xn plus 1 term. So an plus 1 square would be, looking at this expression, we are adding xn plus 1 to the first bracket, and then we add 1 over xn plus 1 to the second bracket. So an plus 1 square is this thing, which you can expand as just by expanding cd plus this, then plus 1. So the nice thing to note is that, well, cd is already evaluated as k square by assumption. And then the question is, can this thing be k plus 1 squared? So remember, we are trying to say, can we be so unlucky that an plus 1 is actually only 1 larger than an, so there's no gaps, right? So the natural question to ask is, okay, what are the conditions required for this to be k plus 1 squared? And by comparing the terms, we see that we need this thing to be 2k, right? And now if we think about it, it's quite natural to then use AMGM on this part, because if you use AMGM, the xn plus 1 cancels out and you get product of CD, which we know how to write in terms of k. So specifically, if we use AMGM, we have this expression here, greater than or equal to 2 square root CD, which is 2k. So actually, it is possible for an plus 1 squared to be k plus 1 squared. But the thing is, this happens with equality if and only if xn plus 1 squared equals to COD, because the AMGM happens to give equality if and only if the two terms are equal, right? So by equating the two terms here, we get this requirement on xn plus 1. So if we multiply C top and bottom, then you get C squared over CD, and CD is K squared. So basically, we reach a very powerful conclusion, which is that, well, in order for an plus 1 to be just 1 bigger than an, we need xn plus 1 to be equal to C over K, where C and K are defined as in terms of the terms here. So that sounds a bit sad because we need to force gaps in order to prove this inequality, and we currently do not have the case that there is necessarily gaps. But then the next natural question is, okay, you can have consecutive terms, but can you get doubly lucky? So can you get double consecutive terms? And this is a natural investigation. So let's take a look at what happens if we have double consecutive terms. So as we said before, if an is k, in order for an plus 1 to be k plus 1, then xn plus 1 must be equal to c over k, where c is this thing here. Okay. Then what happens if we look at an plus 1 and we force an plus 2 to be 1 larger? Well, we have already done the analysis, so it's just a matter of substituting the right expression into the different terms. So if we call this c prime and this is d prime, then by the exact same analysis as before, in order for an plus 2 to be 1 larger than an plus 1, we need the next x term to be c over k, except in this case c is c prime and k is k plus 1. So this is now the requirement if we want to have this an plus 2 to be 1 larger than an plus 1. And what is c prime over k plus 1? Well, we can substitute in c prime as c plus xn plus 1, which is x over k. So we have this thing over k plus 1. And if we extract out c over k at the top, we get c over k times k plus 1, which cancels with the k plus 1 below. So we get this equals to c over k. So this means that if in order for me to have an increase by 1 in the next step and increase by 1 again in the next step, we need both xn plus 1 and xn plus 2 to be the same element. And this is a contradiction because each of these terms here are pairwise different positive real numbers. So that's once you reach this conclusion, you are pretty much on your way to finishing a problem, because now you know that for every 2 steps, there must be at least a gap between the 2 steps, right? So this means that an plus 2 is at least an plus 3. And once you have this, you can very quickly check, okay, a1 equals 1. And this means a3 is at least 4, a5 at least 7, and so on. And this gives a2k plus 1 is at least 3k plus 1. And so this shows you that a2023 is at least 3034. So that's all there is to problem 4. I think it's a very cute little inequality problem. Let me know what you think about this problem in the comment section below. Okay, right now let us move on to problem 5, which is a combinatorics problem. There are a few contestants who have said that this is a really awesome combinatorics problem and they are in love with this problem. So let's take a look at this problem. Okay, we let n be a positive integer. A Japanese triangle consists of 1 plus 2 plus dot dot plus n circles arranged in an equilateral triangular shape, such that for each I, the ith row contains exactly I circles, so basically this shape, and such that exactly one of each circle in a row is colored red. So basically this pattern here, at least exactly one circle in a row will be colored red. A ninja path in a Japanese triangle is a sequence of n circles obtained by starting in the top row and then repeatedly going from one circle to one of the 2 circles immediately below it, and finishing in the bottom row. So basically, for example, from here, you can choose here or here. So you go down, let's say here. Then next step, you can choose this or this. So in this example, you move here. Then next step, you can go here or here, and so on until you reach the bottom. So this diagram is actually given in the contest question as well as part of the question. So it helps to understand, it helps the contestants to understand the problem. Now the thing is, the question now is in terms of n, find the greatest k such that in each Japanese triangle, there is a ninja path containing at least k red circles. So basically, even in the worst case scenario of a very unfriendly configurations of the coloring, I'll be able to find a Japanese a ninja path that covers at least k rate circles. I need to find that greatest possible value of k. Okay, here is some motivation on how you might reach the solution. So the thing is, you need to consider what are the unfriendly configurations of coloring that will make your life difficult. It will make it very hard for you to cover many red circles. So if you have something like a red circle here, then if you want to make your life difficult, your next row you should put a red circle somewhere far away with a gap. So you cannot, your ninja path, right, cannot immediately jump to somewhere far away. It can only go here or here. But the thing is, if you make your gap super large and you keep having your gaps bounce back and forth, right, actually is also not so bad, because even if you miss this row's rate, you can end up collecting the red circle in the following row, for example. So the really unfriendly configurations are those where you introduce a gap just barely enough for you to be out of reach on your ninja path, and then after that you again introduce a gap just barely enough for you to be out of reach from your ninja path, and so on. You spread your gaps out so that you don't allow like following layers or subsequent layers to also overlap and have a chance to pick up the red circles. So this is really unfriendly, because out of these 4 rows, you can only pick 1 red circle. So once you have this idea, it will be quite easy to see that some unfriendly configuration will look something like this, where you basically keep introducing tiny gaps until you hit the other edge of the triangle. Then you start all over again and you introduce all these tiny gaps again until you hit the edge of a triangle, and so on. So let's formalize this ugly, unfriendly configuration and find out what is the bound that we can set for k. So for one direction, I'm going to claim that therefore the greatest k is only at most floor of log to base 2 of n plus 1. And the proof of this is basically using the construction that we just showed on the previous slide. So in order to write this down concretely, basically we are going to number the circles in each row I from left to right, numbers from 1 to I. And what we notice is that a ninja, what is it called? A ninja path, right? When you're standing on a J circle in a certain row, then the next valid transition is either the J circle or the J plus first circle of the next row. So your number really moves either to the same, or you only can increase by 1. So now let us consider the Japanese triangle, where the coloring is at the positions that basically is described by a diagram that we saw earlier. Basically we divide into blocks, and then for the block you start from all the way on the leftmost circle, and then you introduce a gap. You color the first circle, then a third circle, 5th circle, 7th circle, and so on, until you hit the rightmost, which is seen by the position number. Your position must be at most the row number, right? So once you hit and cannot go any further on the right, you start again a new block and go 1, 3, 5, 7, and so on again until you hit the right side again, and then you start a new block again, and so on. So this is the coloring pattern that we will use, and it's quite easy to describe this in terms of formulas if you wish. But basically, once you have this coloring configuration, then firstly you can very quickly and easily check that regardless of what n is, this configuration, right, there will be floor of log to base 2 of n plus 1 number of blocks. And the ninja path can only cover at most 1 red circle per block. And the reason for this is because we saw earlier that each step moves from j to j or j to j plus 1, which means that the number of if you have like the change in position here being greater than the change in the number of rows, you will not be able to hit 1 red circle to the next red circle, because like for example from 1 to 5 here, you only have 2 rows, but your position increased by a difference of 4. But with 2 rows, you can only at most increase your positions by 2. So because of this inequality here, by construction, which is achieved by construction, we will not be able to cover more than 1 red circle per block. So this proves this inequality here, which will probably give you 2 marks out of 7 for problem 5. And the trickier part is to show the other side of the inequality. So we need to show that no matter what Japanese triangle you're given, you'll be able to produce a ninja path that can cover at least this number of red circles, okay? So the key idea here is to actually use recurrence. And why would recurrence be useful? Well, recurrence will give you a meaningful way to understand what is the most number of red circles you can possibly achieve if you perform optimally. Now, how we'll set up the recurrence is as follows. Let us fix n and we fix the Japanese triangle that is given to us. We are going to define Aij to be the largest number of red circles that a ninja path starting from row I circle j can cover. I'm going to call this semi-path because technically speaking, I'm not starting from the top. I'm starting from row I circle j, and then I'm asking myself, including this starting point here, what is the largest number of red circles I can cover if I follow the rule of the ninja path going like either left or right each time I go downwards. Okay, so why would this recurrence be useful? I mean, why would this definition be useful? It's because we can very easily set up a recurrence to understand how Aij can be calculated in terms of the two circles below that. So in fact, because from this starting point, I can either choose to go left or choose to go right. So from the left or right, I can recursively look at the best possible path. So Aij is given by the maximum of either the left option or the right option. And then not forgetting the scenario where my start point is a red circle itself, then I will add 1. So this is the indicator function, which is it will be equal to 1 if the circle at ij is red and it's 0 otherwise. So this recursive formula is quite easy to define, which gives you a natural idea of how to proceed. So the thing is, well, you know, in the bottom row, it will be all zeros except one of the circle is 1, right? Because that one circle that is red, obviously it can cover one red circle, and the rest there's no chance of any red circles, it will be 0. And then the thing is, can I use this recursive recurrence relation to bubble upwards and calculate the circles of the next higher row, then next higher row, and so on, all the way to A11. And then hopefully A11, which is the answer that we want, is greater than or equal to this. Well, it turns out that bubbling up individual elements is quite difficult. It's much more easier to bubble up by layers in this scenario because you are only given information about layers. So for example, the bottom row, you know there's one red circle somewhere in the layer, but you don't know where. And similarly for the rest of the layers, you know there's exactly one red circle in the layer. So the thing is, how do we define a quantity using this recurrence that can bubble up layer by layer to the top layer? And this is where the clever solution comes in. I'm going to define for row I will define its summarize sum to be you raise 2 to the power of the a value of each circle, and then you sum them. So 2 to the power of ai1, 2 to the power of ai2, and so on until 2 to the power of aii, and you sum them. And you might ask, why this weird 2 to the power of something? Normally, if you think about invariant or monovariant for a row, maybe you just take the simple sum of the a values. But in this case, the motivation is because you know the answer will involve log to base 2 somewhere. So if you define the summarized sum like this, the summarized sum in the top row will be 2 to the a11. So if you can bound 2 to the a11 in terms of something, then a11 will be bounded in terms of log to base 2 or something. So that gives you an idea that this might be a useful thing to consider. But more motivation will come shortly. And the main claim that we want to show is essentially that the summarized sum will increase from one layer to a higher layer. So basically, we want to show Si is greater than or equal to Si plus 1 for all I. And this will complete the proof because S1 will then be bigger than or equal to the next row S2 and so on until Sn. And Sn is something we can calculate because as mentioned before, all the A's will be 0 except for the red circle whose A value will be 1. So in that case, it will be like all the terms will be 2 to the power of 0, which is 1, except one of them will be 2 to the power of 1, which is 2. So you get n plus 1 here. And so A11 will be log to base 2 of n plus 1. And given that A11 must be an integer, this actually, you can check that this forces A11 to be greater than or equal to the floor of log base 2 and quantity plus 1. So this is another motivation that another signal that this will be a useful definition to consider. And now let us now move on to the main claim. So all that is left now is to prove this main claim. And the proof of this is actually quite clever if you think about it. It's not a complicated idea, but writing down in symbols might make it look a bit more complicated. So try to stick to the main idea. Okay, so over here, just to recap, we can calculate Aij in terms of max of the left or right option, and then plus, and you have a plus 1 if and only if that starting circle is red. So what we're going to do is first ignore the operation where we have a plus 1 if and only if the circle is red, meaning I have the A values for the row I plus 1 already, and pretend temporarily for a moment that Aij is calculated by just looking at the max of the left or the right option. Then what we have is, if we take 2 to the power of the a's, again the 2 to the power of a quantity is bigger than or equal if you look at the left version or the right version. Okay, so nothing too complicated here. And the clever idea is we are going to try and map each circle in the ith row to each circle in the I plus 1 row. And we have an extra circle here, so what we are going to ignore is we are going to throw out the circle with the least value. So define M to be the index where the A value of that circle is the lowest among those in the row. Okay, and then what I'm going to do is, for each of the circle in the I row, right, I'm going to look at the left, look at the left, look at the left until I hit M, then I'll start looking at the right. And what this means is basically the 2 to the A value of this thing is bigger than or equal to if I look at the left. Then the 2 to the A value of this thing is bigger than or than the value if I look on the left. And then same thing for this circle, then if I look at the left. And then the 2 to the A value of this circle is bigger than or equal to the 2 to the A value if I look on its right child. So by having this one-to-one mapping, we can check that the sum of this row will therefore be bigger than or equal to the sum of this row, except you threw away the M circle. So in this case, Si is bigger than or equal to Si plus 1 minus the value of the M circle that I threw away. So it's 2 to the Ai plus 1 comma M. Okay. So far we have ignored this plus 1 if and only if red rule. So now we include back the consideration of doing this rule. So what happens when you include back this rule? Well, actually for most of the circles, the A values wouldn't change, because if it's not red, right, it will be the A value is already the calculated. The only one circle that will change is that red circle in the row, and for that particular index J, right, the value of A will increase by 1. So if you look at 2 to the power of A, when now the value of A increased by 1, this is basically doubling the original 2 to the A. So basically, when I add back this rule, the change that you have on Si is that it will increase Si by 2 to the A for that particular index J whose circle is red. But the thing is, 2 to the Aij for that circle is bigger than or equal to me looking to the left or to the right of the child, and that circle, right, in particular is also bigger than or equal to the smallest value circle in that row. So because of this inequality now, if I increase Si by 2 to the Aij, then this right hand side will also increase by 2 to the Aij, which will definitely at least outweigh this thing. So now we have the correct Si value is bigger than or equal to Si plus 1. So that is all there is to this proof, and take a while to digest this proof of the main claim, which I think is a really brilliant and neat little proof, but it might look a bit complicated when you write it down as symbols. So what do you think of problem 5? Let me know in the comment section below, and I think hopefully you agree that this is also one of the more beautiful combinatorics problem that you have seen. Okay, let us now take a look at problem 6. And problem 6 is a monster geometry problem which only 1% of the contestants managed to get full score on. You will see this in the statistics section at the end of this video. So without further ado, let's take a look at problem 6. And while the solution is a bit long, hopefully it will be easier to understand this through a video, because I will show you the different angles that pop up in the proof in a visual way. Okay, so as usual, I will pause after each statement to show you which segment of the diagram has just been described by the problem. So over here, we have ABC is an equilateral triangle. And then we let A1, B1, C1 be interior points of ABC such that BA1 equals A1C, CB1 equals B1A, AC1 equals C1B, and the sum of these three angles is 480. So we have A1 such that this line, this segment is equal to this segment. We have B1 such that this segment equals this segment, C1 such that this segment equals this segment. And these three angles over here sum to 480 degrees. Okay, and then now I'm going to let BC1 and CB1 meet at A2, and let CA1 and AC1 meet at B2, and AB1 and BA1 meet at C2. So basically, I'm going. So remember, I have this point here, right? If I extend and I extend this will be B2, and then if I extend the B thing and then I expand the C thing, this will be A2, and then if I extend this B1 and then I extend this A1, it will meet at C2. So I just define A2, B2, and C2. Okay. Now prove that if triangle A1, B1, C1 is scalene, then the three circumcircles of the triangles A, A1, A2, B, B1, B2, and C, C1, C2 all pass through two common points. So we have A, A1, A2 here. The circle is probably too big to be shown on this slide. And then you have B, B1, B2 again, the circle is some giant circle. And then C, C1, C2. Basically, we need to prove that the three circles all pass through two common points. Okay. So to start off this problem, we'll do some basic angle tracing first, which will then help to inform what would be a suitable approach to take for the future steps. So for a start, let's do something with this 480 degrees. By the fact that these are isosceles, I can introduce alpha, alpha, then beta, beta, gamma, gamma. And by angle chasing the 480 degrees in that three triangles, we can see that alpha plus beta plus gamma, it will be 30 degrees. So this is just basic computation. And the thing is, I want to now show that actually there's something I can say about the triangle BA2C. Okay, let's take a look at this triangle. If you look at this angle over here, this angle is basically in this triangle, right? Minus the angle here and the angle here. And the angle here is 60 minus gamma. The angle here is 60 minus beta. So I can write this angle here, BA2C, as 180 minus 60 minus gamma minus 60 minus beta. And by substituting the earlier equation, I get 90 minus alpha. So this is 90 minus alpha. But the nice thing is this angle here is 180 minus 2 alpha. So this angle here is half of this angle, which suggests something about the center being A1. And indeed, because A1 lies on a perpendicular bisector of BC, as you move along a perpendicular bisector, the unique point such that the angle subtended equals to double of this angle must be the center of the circumcircle of BA2C. So what we have just shown is that A1 is the circumcenter of BA2C, and completely analogous statements can be made for B1 being center of this and C1 being center of this. Okay? So I'm just going to record down one copy of this result over here. But remember that it applies symmetrically across the different letters. Now what we are going to show is that these 4 points, the B and the C's, are concyclic. So B1, C1, B2, and C2. And to do this is actually quite straightforward angle tracing. essentially C1 is the center of the triangle here. So these three lines are all the radii, right? So this angle will be equal to this angle because of isosceles. And then similarly, B1 is the center of that circle. So these three lines are the radii. So this angle equals this angle. So from which this angle equals this angle, which shows that these 4 points are concyclic. So we have these 4 points are concyclic, but completely analogously, we can say that C1, C2, A1, A2 are concyclic, and A1, A2, B1, B2 are concyclic. And this is a very striking observation, because if we look at the first two statements, C1, C2 will therefore be common points that lie on the two circles that circumscribes this, right? So C1, C2 is the radical axis of the two circles that circumscribe this. And then similarly, A1, A2 is the radical axis of the two circles that circumscribe this. And similarly, B1, B2 is the two circles that is the radical axis of the two circles that circumscribe these two. So we have pairwise radical axis of three circles. By the radical axis theorem, A1, A2, B1, B2, and C1, C2, which are the three radical axes, all meet a common point P. Now, there's a little trap here that you need to check. If you never check, you might end up getting subtracted 1 mark, which might have happened to some of the contestants. I don't know why they got 6 out of 7, but you need to be careful that and check that it is not the case that A1, A2, B1, B2, C1, C2 are actually the same circle. Like these three circles might be the same circle if all the 6 points are concyclic, and then you will not have this statement here. So, but it's quite easy to check this because basically the sum of the alternating alternating angles are equal to the sum of these three angles, which is 480, is given in the question. And for a hexagon that is inscribed in a circle, the sum of the alternating angles is equal to 360 degrees. This is a theorem which you can either look up or it's quite easy to prove by angle chasing. So in either case, we managed to show that this scenario doesn't happen. So indeed, we have the three lines are radical axis and they meet at P. And P is a very useful point because now we take a look at the original question. We need to think about these three circles. But P lies on A1, A2. And if you look at the power of P with respect to the circle A1, A2, right? Well, the definition is that the power of P will just be PA1 times PA2. So similarly, the power of P with respect to the circle circumscribing BB1, B2 will be PB1 times PB2. And same thing for power of P with respect to the circle circumscribing C1, C2. And the thing is, because of these concyclic properties, PA1 times PA2 by this statement here is also equal to PB1 times PB2. So because these are concyclic and lie on the same circle, this expression equals this expression. And similarly, because of this, this expression equals this expression. So in summary, we have just shown that therefore P has equal powers with respect to each of these three circles. And this is very powerful because it suggests one idea, that if basically P lies on the radical axis of these two circles, and it lies on the radical axis of these two circles and radical axis of these two circles as well. If we could find another point Q with equal powers with respect to the three circles, then basically the line defined by PQ must be the common radical axis between the three circles, which will then sort of give you this picture here. So there is still some cleaning up that you need to do, which I will only clean up at the end of the proof. But this idea here is just a motivation. So from the fact that P has equal powers with respect to these three circles, it inspires you to maybe find another point Q that have equal powers with respect to these three circles. So let's keep this green box in mind. It has already been proven, and embark on the yellow box. So to do this, I'm now going to actually play the same game, except instead of using the A1, A2, B1, B2, and C1, C2 intersecting at P, I'm going to construct a new point A3. And then I'm going to make A, A3, B, B3, and C, C3 all intersect at a common point Q. So the construction for A3 it looks a bit weird, but the motivation of it will become clearer. That is a nice point as we go through the proof. So I will construct A3 by basically taking the line AA2, okay, and then I have the line AA1 here, which is the perpendicular bisector, right? I reflect the green line about the perpendicular bisector. So I have this new reflected line, and I let that reflected line intersect the circle A1, A2 at the point A3. Okay, so this circle is one of the circles that we care about, the A circle. And then basically I'm taking this line reflect about perpendicular bisector and see where it intersects the circle that we care about. I call that A3. And okay, I'm going to just put the point A3 here and remove the construction lines because that will clutter the diagram. But basically to remind you of the construction, we have AA2 is corresponding to AA3 once the lines are reflected across AA1, okay? And the other thing is A2, A1, and A3 are concyclic by constructions. So similarly, I'm going to construct B3. Basically, I take B2 reflect about perpendicular bisector and see where it intersects the B circle. And same thing, C2 reflect about the perpendicular bisector. I get a line and I see where it intersects the C circle. Okay, so I construct B3 and C3. Now, A3 might look like a random point and too creative to be conceived, but there's something nice about A3. There's a lot of properties about A3 actually. So one thing about A3 is, let's take a look at the A circle, okay, and see what do we have. So this is the A circle. Recall that the A circle AA1, A2, but A3 is also defined by taking the line and intersecting the circle, right? So A3 lies on the circle. So these are concyclic, and this thing is that AA2 and AA3 are mirror images around AA1. So actually this purple angle is equals to this orange angle over here. And by the concyclic property, this purple is equal to this purple and this orange equal to this orange. So actually, these two angles are equal. So A1, A2 is equals to A1, A3. And A1 is not just any random point. A1 was your center of this circle, remember? You have A1 is the circumcenter of B, A2, A3. So A1, A2 is the radii, and now we establish that A1, A3 is the radii. So actually, A3 is also concyclic with B, A2, and C. So how some contestants might have conceived of the idea of constructing A3 is the other way around, where they look at the circle A, A2, C, which we already have some information about, and see where it intersects A, A1, A2, and they define that point of intersection as A3, and then they notice that AA3 is a reflection of AA2 about the perpendicular bisector. So in any case, we know this nice other property about A3, which I'm going to record here. And again, the corresponding statements for B3 and C3 holds. Now, as I mentioned before, the name of the game here is we are going to hope that we can make the statement that B, B3, C, C3 are concyclic and so on. Then AA3, BB3, and CC3 are radical axes that meet a common point, which we shall call Q. The thing is, now let us try and prove this concyclic statement here, which we want to prove. So we want to show B, B3, C, C3 as concyclic, right? So these are the red points here. And the proof of this is actually quite clever. Let's take a look at the angle BC3C, okay? To prove that the 4 points are concyclic, I'm going to show that BC3C is same as BB3C. Okay, so this angle subtended is equal to this angle subtended. But thing about BC3C is, well, I'm going to introduce a point C2 prime by taking C2 reflected about the perpendicular bisector here and call it C2 prime. And why I introduce this C2 prime? Well, firstly, the line CC2 when reflected give you CC3, right? So CC2 prime and C3 is actually a straight line. So the angle BC3C is the same as BC3C2 prime. It's the same line. Yeah. So I'm now looking at BC3C2 prime, and why I move the point C to C2 prime is because now I have I can now focus my attention on these 5 points over here. Now, C2 prime is actually lying on the circle that contains these 4 points. So we already saw earlier that these 4 points are concyclic, right? And C2 prime is the reflection of C2 across the perpendicular bisector, and so is A and B. And this perpendicular bisector bisects this chord. So if you reflect C2 about the perpendicular bisector, C2 prime also lies on the same circle that contains ABC2. So we have these 5 points which are concyclic, and BC3, C2 is the angle we are after, and that would be equal to BAC2 prime. So once again, angle subtended by B and C2 prime will be equal to angle subtended by B and C2 prime. And why I bring it into our main triangle is because now we can use the symmetrical setup of AB and C2 prime to transfer this angle over to the other side. So BAC2 prime is same as ABC2. And ABC2 is basically just 60 degrees minus alpha. So that converts the angle that we are after into something that is much more tangible that we already have, 60 minus alpha, this angle here. And a completely analogous argument for B3C, remember this is the other angle we are interested in. Again, you introduce the reflection and convert into this angle and then use these 5 points. You can show that the angle we are interested in is now equal to this angle here, ACB2. It's a completely analogous argument. And this is against 60 degree minus alpha. So from these 2 statements, we have proved that the 4 points, BC3, B3, and C are actually concyclic, which is what we wanted to prove. And again, the statements hold across the different configurations of the alphabets. So we have these 3 statements here. So once again, the radical axis are AA3, BB3, and CC3, and they all will meet at a corner point Q. Except you again need to check for the trap that what if the 6 points are actually lying on one single same circle. But that's quite easy to check because we already shown, for example, that the angle subtended BC3C, this angle subtended here, BC3C is equal to 60 minus alpha. That's from the previous slide. And that is different from the angle subtended BAC, which is 60 degrees. So definitely these 4 points are not concyclic, and therefore they all don't lie on a single circle. Okay, so once we check this, then once again, by completely analogous argument, recall that B and B3, for example, lie on the circle B1, B2, right? So if you look at the power of the point Q with respect to that circle, is QB times QB3, and again that's equal QC times QC3, and equals QA times QA3, and so on. So Q has equal powers to basically the 3 circles of interest. So we now have found our second point, but do we know that they are actually distinct points? Why P and Q are the same? Well, actually it's again quite easy to check. Basically, recall P lies on A1, A2. Sorry, this should say P lies on A1, A2, not AA2. And Q lies on AA3. And A2 is on one side of the perpendicular bisector. A3 is on the other side of the perpendicular bisector. So, and A1 and A are on the perpendicular bisector. So P lies on one side and Q lies on the other side of the perpendicular bisector, and therefore they must be distinct points. So again, this is supposed to be A1, A2. So after a glorious long journey, we are finally on the last slide. There's a little bit of work left to do, because what we have shown so far is that the line defined by PQ is the common radical axis of the 3 circles, but this does not yet mean that the 3 circles will all pass through 2 common points. There are a few corner cases we need to rule out. So for example, if all the 3 circles are tangent at one point, that will still have a common radical axis. So to rule out these corner cases, what we would like to show is that actually, firstly, there is a point that exists strictly inside each circle on the radical axis. So in this case, the point P lies on A1, A2, which is a chord in the circle. So the point P is the example of a point on the radical axis that lies strictly inside the circle. And this holds for the second circle and the third circle as well. And why do we want to show this? This is because this shows that each pair of the circles must intersect at 2 points. So for example, if you have two circles, the possible configurations of the two circles and the radical axis are shown here. And this is the only configuration where there exists a point on the radical axis that lies strictly inside the circles. For example, all the other configurations, there's none of the points that will lie strictly inside the circle. So all these are ruled out. So if you have each pair of circles, they must intersect at 2 points. Then let's look at our scenario here. The first two circles will definitely intersect at 2 points. Then where can the third circle intersect the first circle? So the third circle must intersect the first circle at 2 points, and that 2 points will define a radical axis which must coincide with the first radical axis here because of what we have shown. They have a common radical axis. This means that the points of intersection which are on the circumference of the first circle must have no choice but be the same two intersection points as before. So, phew, after a very long journey, we have finally finished proving the question. What do you think of this monster problem? Well, there are certainly a lot of steps, so that's why the statistics which we will get to at this point shows that problem 6 is really harder than the previous year problem 6. So over here we have the statistics of the 6 problems of the IMO. Let's take a look. There are some really interesting facts about the statistics this year. So the first thing that is the most jarring is that problem 1 has a much higher mean and percentage full solve compared to the previous 2 years. And indeed, many people say problem 1 this year is like ridiculously easy, right? So you can see it in the statistics here. Not everyone got full solve, but it's still higher than previous 2 years. Problem 2, on the other hand, is slightly harder than previous year. I think this percentage is a expected percentage for problem 2, because I remember last year we said that problem 2 was ridiculously easy for problem 2, and the year before problem 2 was that super weird like real analysis problem which like killed everyone. So I think this year's problem 2 is of a suitable standard. Problem 3 has a surprisingly high percentage compared to the previous 2 years. I thought it was quite involved, but still an interesting problem. So but there are some contestants who did say that P3 is like a hard P2 rather than like a full-fledged P3. P4, I guess, looks reasonable compared to previous years. And P5, this is quite interesting. So P5 was the Japanese triangle question. I thought it is of a suitable standard, but it turns out that P5 is actually much harder to get full score on compared to previous years. Who knows, maybe the idea of coming up with the monovariant of the layer is really difficult to inspire. And lastly, P6, even though it's the hardest problem of each year, this year's P6 is really, really, really hard. The geometry has a lot of steps involved, and some of the steps are not easy to motivate. So we only see 1% of the contestants solving it compared to previous years where there's a bit more contestants solving it. So that is all for today's video. What do you think of this year's IMO problems? Let me know in the comment section below. Stay tuned to the channel for more math videos, and see you soon.